Okay. Hi everyone. Hi, how are you? Good. Okay. So, any question? No?
Yeah.
Yes.
Is it possible to have two maximum solutions?
Two maximum solutions. What do you mean by two maximum?
I can't be as more specific than that actually at this moment.
Twos. If you mean a solution for X, a solution for Y, of course you need to have that because.
Why?
Okay.
Why? Two alternate solutions that both fit both of it.
Yes, you might have some objective function which is maximized in two different solutions or minimized in two different solutions. So it is possible to have multiple solutions.
It is possible.
Yeah, as long so if your objective function is not convex, then of course it is possible to have several argmin or several argmax, right? Yeah. So, any other question? No? Okay. So, someone, before we start this session, we are going to talk about reinforcement learning. But before we start, someone asked very interesting question in Piazza. I thought about it for days. And I think it was one of the most interesting questions that I signed this semester. And that was this. Okay. So, it's asked by anonymous student. Okay. So they ask that we have mentioned that for Nash equilibrium, we said a way to find the Nash equilibrium in a game is to this slide. Do you remember this? So it was to start from one of the cells in the game matrix and move or deviate to an adjacent cell. So the question is about this adjacent part, and says, so the discussion that that person has mentioned is very interesting. So first off, I should say that I need to rephrase this. Just this adjacent is correct to say if we have two actions per player, right? Then if we have two actions per player, the actions are adjacent to each other, the possible actions. But if we have three actions, then what happens? Consider this example. So I have action A, B, C. Okay. Then also here I have action D, E, whatever, right? So the payoffs are important to me. Assume I have, let me think. So 1, 2 here, and 3 here. Yes, okay. And whatever here, something here, I don't care, okay, for now. So assume I want to find the Nash equilibrium, draw the deviations. Assume I'm in this cell, right? Then 3 is greater than 1. I move toward this. What about moving from B to A or A to B? 2 is also greater than 1, so I move here, right? As a result, depending on the payoffs of the first player 1, player 2, this part might be a weak Nash equilibrium or strong or weak, whatever, or it might not be. Again, it depends on whether we have this arrow or this arrow. Assuming that we have this arrow, then this becomes a Nash equilibrium. But the person asked that 3 is greater than 2, and we know that the order of the actions does not matter, right, in the matrix. So you can say ABC, ACB, whatever. So as a result, if the person is here, player 2 is here, then they will also deviate to here, right? Because 3 is greater than 2. I'm discussing it with you. If you have another opinion, let me know. Is that person right? I think they are right. All right? So as a result, because you can shuffle A, B, C, A, C, B, B, A, C, whatever. So sorry about my phrasing, and also I made a mistake in my explanation. I should say that you should compare every 2 pairs of the actions in the matrix. So for example, here, A is not stable for P2, player 2. Player 2 wants to deviate to this cell because 3 is greater than 2. Okay, so that's one thing you should notice. Again, this explanation is correct, including the adjacent word, if we have 2 actions per player. But if we have more than 2 actions, then you shouldn't say adjacent cell. You should say to any other possible action of that player. Okay? Did you get it? Is it clear now? Right? Okay. So that was one thing I wanted to mention. A correction, and I thank that person a lot. It was a great question. So now let's talk about the start reinforcement learning, fundamentals of reinforcement learning. So first off, I should confess that I'm not an expert in RL, reinforcement learning. Okay, so I don't know everything in this area. Of course, I don't know everything in anything, but at least in this area, my lack of knowledge is a bit more. Okay, but I will let you know whatever I know. This is my duty to know whatever I know, to let you know whatever I know. So hopefully I can teach it well. And this is the first time I'm teaching RL, okay, in my life. So, but it's a very interesting topic. Usually in AI, people who work in RL, they don't work in the statistical machine learning area. The people who work in the statistical machine learning area, they don't work in RL. Usually they are disjointed. But I think we still need some people who work in both areas. But there are some exceptions. For example, Yashua Benjel works in everything, right? So there are some exceptions. There are some monsters in AI who work in all different areas. And apart from those people, I'm saying that. Okay, introduction. So reinforcement learning, by the way, interrupt me whenever you have any question or comment or opinion. You might know better than me in this topic. Okay, so reinforcement learning, or in short RL, is an area in machine learning where one or several agents take actions in an environment, okay, in an environment to maximize their cumulative reward. So I will explain all of these things. First off, let me tell you that reinforcement learning is exactly the same thing that the same day that we train animals, such as dogs. Okay, how do we train animals or dogs? For example, I want my dog to come to me whenever I come home. Okay, the first time I buy a dog, then I come home and the dog doesn't move. I will not give food to that dog for some hours, right? So hunger or not giving food will be a negative reward or a punishment for that dog. If I do it, so maybe for the first time, the dog will not find any correlation between these two, right? After several repetitions, several days, this happens, and I don't feed the dog. Suddenly, one day, the dog randomly comes to me when I come. Then I give food to that dog in that day. Maybe the dog still is in doubt whether there is a relation between coming to me and getting a positive reward or food, right? The next day, it will try again, see what happens. Comes to me, and I again give food. So by some trials and error, the dog will find out that there is a correlation between having food, positive reward, and coming to me, right? As a result, it will learn to come to me whenever I come home, right? This is the way that they teach animals, both pets, home animals, and also the animals in zoo. You have seen lions which stand on their feet, right? Or the lion plays with its owner, it doesn't eat the owner, right? So how do they do that? In zoo, they also teach animals in this way. For example, they have a stick, and whenever the animal comes and grabs the stick, they will feed it. So the animal will learn to stand up and grab the stick, right? So they will do it in zoo in front of people as well. So now in the era of AI, people said, why not assuming that artificial intelligence is a dog? Okay, let it be a dog or an animal. So I want machine to be my dog, and the machine initially will do some random interactions, right? Randomly, doesn't know what is good, what is bad to do. And then after some time, some trials, some iterations, the machine finds out that apparently there is some correlation between doing some things in some states, in some situations, and positive or negative rewards, right? As a result, the machine learns to do some good things in some specific situations to get positive reward. But how can we do that? How can we, you tell me. So this is the concept. Put yourself in the shoes of the designers of RL. So you know that you have some positive reward, some negative reward, and you have some actions to do, right? How should we implement it? Do you remember that famous sentence that I always say? Yeah. So this was in English, right? Now, how do we implement it in mathematics? So I have rewards, I have actions. You have a function. Okay, so you have a function, an input and output, okay? Okay. Okay, so you're saying that you will have a function for reward. That's correct, okay? And then what do we do with this reward? This is the way that you should learn algorithms. Put yourself in the shoes of the designers. Okay, so first up, policy. Policy means what to do, right? What actions to choose. So the reward adjusts your policy, but how? How does your reward adjust your policy? Different algorithms. What do different algorithms do? What is the backbone behind different algorithms? So we have some reward, some policy. Policy means what to do in different situations.
The existing state on which they make decisions based on the current.
So
based on what something happened, they adjust their current.
So I'm saying that you're saying it in English, right? Just so you're saying that, so we have some state. State, it means situation in the environment. We have some reward, we have some policy. We want to see whether if this action, so policy determines the action, right? If this action is good, it means that the policy was good. So you need to give good reward for this situation and this action, right? But how do we do that? Optimization, I guess. Everything is optimization, right? You need to define some cost to minimize, right? So, as I said, this is my famous quote by me saying that all machine learning is optimization plus some other stuff, such as linear algebra and probability. So if you take away optimization from machine learning, nothing remains. Okay. Everything is optimization. So you need to either minimize a cost function or maximize something. And we'll see that we'll also have optimization. So you have some concept and you implement it using optimization. So here, Thank you, by the way, for answering. Please answer me and let it be interactive. This is the best way to learn. So we have some agents or players. So as you see, there is connection between reinforcement learning and game theory, right? In game theory, we have players or agents. Here we also have players and agents. That's why many of the RL researchers also work in game theory. There are a lot of theses which have combined these two areas. Yes. With control? Yeah, I believe so. But I'm not that much expert in that area, but I believe that yes, because in control theory you also have agents, plants, actuators, and these things. But I think you guys know better than me. You know control theory better than me. I only have passed several courses during my undergrad for control. I passed linear control, digital control. Yeah. Yeah, I also have passed their labs. But yeah, my knowledge in the area of control is this, plus some other things such as fuzzy logic. And we'll cover fuzzy logic in this course, by the way. And yeah, so, but as far as I know, yes, you can combine the area of reinforcement learning with control theory as well. So you see, you shouldn't restrict yourself to one specific part of science. Fields of science are related to each other. So we have agents or players which play, and we have some actions. We have some environment. Environment means what situation. So we have some environment. This environment can get different situations, right? The situations that the environment can get is called a state. So for example, this is a state. I can ask you to stand up and shuffle your seats, right? That's another state, the state of the classroom, right? So the classroom is environment, but where you guys sit is a state of this environment, right? Or situation. State is situation. And agents here are you, for example, you guys, right? Actions is what you do. Whether you stand up and sit there, this is one action. Whether you stand up and sit over there, that's another action, right? So we have possible actions. We have reward, and reward means that if this action was good, we give you positive reward. If it is not good, we don't give you a reward, or negative, we give you negative reward, right? And why is it called cumulative reward? Yes. Yeah, you sum it, but exactly, because you sum it. But why do you sum it? Consider, yeah. The store, all the experience you have, but this cumulative reward is for future, for what happens in the future. But as far as I know, this is not cumulative reward so far. This is cumulative reward from now until the end. Let me tell you an example.
Oh, yes, the future reward.
Yeah, the future reward. Okay. So let me tell you an example. Playing chess. Okay. Assume I'm playing chess. In this movement, I sacrifice my queen. My current reward is very bad. Queen is very important in chess. But I know by this sacrificing, I will win in 10 moves. So my cumulative reward is important. What happens in the future, right? But there is a but. That my current reward is scaled more than my next reward, because I see my current reward right now, right? So I have some discounting of reward. Do you remember previous session? We had discounting in repetitive games as well, right? So we have some discounting, and we'll see that. So in other words, RL is learning to make decisions with interactions. So RL is a decision-making process. Right? So what does it mean? By interaction. So the agents interact with the environment, right? So we have some agent, some environment. Agent make some action on the environment, and then they will observe some observation or state from the environment. And based on that action, we can reward, right? We can reward the agent. And what if we have multiple agents rather than one agent? Then we'll have, so it means that soon we have multiple agents which cooperate with each other. And what does it mean? They learn, by the way, when they interact with the environment, what does it mean? They are learning the environment, right? Initially, they are blind. The agents are blind. They don't know what is good to do. They will do random things, and by the rewards, they will find out what is good to do in different situations of the environment. So basically, they are learning the environment, right? But now assume I don't have one agent. I have multiple agents, and they learn this environment together. What do I mean? One agent learns that part of their environment. Another agent learns that another part of their environment. So this agent knows that what should be done in that area. The other agent will learn that what should be done in the other area. And we usually have a central agent because this becomes distributed, right? This becomes distributed. So it's a distributed algorithm when we have multiple agents. And let me tell you that for distributed algorithms, we have at least two main approaches. Okay. One approach is we have a central agent, whatever you call it. It's a central server, right? So we have a bunch of servers or agents, and we have a central server. The servers or agents will do their things, and they will send the information to the central server. And the central server will combine the information and decide and send the relative or corresponding information back to the servers. Okay, so this goes to the central server back and forth, right? What is the issue or flaw of this algorithm? This type of algorithm has some big issue, has some big flaw. Consider a hacker. The hacker wants to, yeah. So yes, but I wanted to say it in other words, but yes. So you're saying that if someone gets input and output to the central server, they will know everything. In other words, I can say, what if the hacker attacks the central server? Then the whole system shuts down, right? So it becomes sensitive to hacking or attacking, right? The result is not good for security, right? With
They care about that when they're developing reinforcement.
They care about it for everything. So, by the way, this distributed algorithm appears in different areas of science. One of them is multi-agent reinforcement learning that I'm gonna explain. The other one is federated learning. Have you heard of it? Federated learning, you have, again, some central neural network. You have a bunch of neural networks. They will, it is iterative algorithm. They will learn with their own data, and they will pass their weights to the central neural network. The central neural network will combine or take average of these weights and send them back to the neural networks. Why do they do that? One of the benefits of this distributed approach is what? Is privacy. So these servers, which were not central, they don't see each other. It's privacy. So this distributed algorithm is good for privacy. But this approach has a flaw. And this flaw is being very sensitive, prone to be attacked, right? As a result, another approach for distributed algorithms exists. And that is, have you heard of peer-to-peer networks? So, for example, so it means that there is no central server, and servers are connected to each other. Every server is connected to several other servers, right? So I send my information to my neighbor servers, then those people send their information to the neighbor servers. As a result, we can communicate with each other through some other servers in the middle. As a result, no one is responsible for everything. So if one of us is attacked, the whole system doesn't shut down. So its security is good, right? So that's one thing. And an example, there are some examples of these peer-to-peer networks. There are a lot, but there are, I forgot its name, and I don't want to say its name because it's been recorded. There is an illegal website for sharing things. No, not that. But just I'll let you know that it's illegal, okay? For the sake of copyrights and these things. So they do that. This is exactly what they do. Why do they do that? Because they don't want to be shut down by the governments and these things, right? So that's one thing. But there are other things in cell phones and these things for. So at least there are 3 areas that we have distributed algorithms. At least there are a lot of. One of them is phone networks. Okay, so telecommunication. Another one is I think internet. I think you can consider it as distributed algorithm. Also, another one is multi-agent reinforcement learning. Another one is federated learning. And these areas, there are a lot. Okay, so basically, multi-agent reinforcement learning, or MARL, is one of the cool areas of RL, where there are several agents which cooperate with each other, and they usually have a central server. One of my friends and lab mates named Shriram. I don't know if you have. So he's also good in RL. His thesis was MARL. He's now a postdoc in Vector. Who else works on MARL in this university? Yeah. Mark Crowley. One of them is Mark Crowley. The other one. So Mark Crowley in ECE department. Also in CS, we have Pascal Pupa. Okay. They work in MARL. So at least we have 2 people in this university working on RL. It is, so as I said, I explained this. And reinforcement learning contains some elements. So these elements, as I said, there are environment. So environment is the environment in which the agents play. So consider the game of tic-tac-toe. Right. So the environment in tic-tac-toe is this left side figure. Okay. As you see, this is the environment. The action which the agents play. So for example, putting a cross is the action of one of the agents, right? So here at least there are 2 agents competing with each other. This is not multi-agent reinforcement learning, I believe. This is one agent competing with the other one, okay? And because you can consider one of them as agent, the other one as human. You can play with machine against machine, right? So state is a state or realization or situation of the environment. The environment has a state at every particular time. At every time, we have some state, right? So, for example, this is one of the states in tic-tac-toe, right? And so the state S, by the way, can be a vector or a matrix representing the state of the environment, right? Let me tell you some examples of how we can have the state S. For example, in tic-tac-toe, the state is a 9-dimensional vector. Why? Because we have 9 cells, right? Every element can get one of 3 values, either cross or circle or empty, right? So how many possible states do we have? 3 to the power of 9. Am I right? Am I right? What about inverted pendulum? Many of you are students in mechatronics, so I think you know better than me. In pendulum, we have 4-dimensional vector state having values for position, velocity, angle, and angular velocity. By the way, do you know what is inverted pendulum? So basically, we have some small car, okay? And there is some pendulum on it which can fall, okay? It's unstable, it can fall. And this car can go left and right. How do we move it in a way that the pendulum never falls? So it's an inverted pendulum and it wants to fall, but we should move this car or cart, whatever we call it, so this pendulum doesn't fall, right? This is inverted pendulum. Can you give me some examples of inverted pendulum in real life? Yeah. Unicycle, what is that? I don't know. Yeah. Oh, yes, exactly. Unicycle. So you know what is that? I think your English is better than me. So you are on a wheel, on one single wheel, and it moves, right? So it's an inverted pendulum, and of course it has control in it. Otherwise, you will fall, right? So that's one thing. Unicycle. Another thing.
Circus. You know, circus.
Circus.
Like guy actually on a unicycle. He like hold like that.
Okay, so in circus, yeah, a guy on a unicycle also wants to control something on their hand, maybe something, or on their mouth, right? Okay, that's another example. But another more serious example is when NASA wants to shoot a shuttle, or right, when a rocket or shuttle, whatever we call it, wants to launch. What do they do initially, in initial seconds? When they count down from 10 to 1, what do? They release some stuff, right? For several seconds, maybe initial 10 seconds, it's an inverted pendulum until the engine fires and it goes up. Before the engine fires and it goes up for several seconds, it is an inverted pendulum. If they don't use a controller there, the rocket will fall before even starting. Okay, so that's a serious problem. And at least for several years ago, I knew that NASA, the controller for inverted pendulum in NASA was a fuzzy controller developed by Lotfi Alizadeh. He passed away. But Lotfi Alizadeh was in University of Berkeley, right? And you know that the University of Berkeley is funded by US military, right? So they invested a lot on fuzzy controller and fuzzy logic, and NASA used that. So I don't know about now what controller they are using now, but previously it was fuzzy controller. Okay. Anyways, where were we? So we have these states: position, velocity, angle, and angular velocity. What about Atari games? So assume we have some Atari. Have you played Atari or Sega? These are older than PlayStation. Okay. So Atari games, they are simple games. They had joystick, and then so Atari games environment or state. Environment is the frame, right? And the state is what we have in the frame, right? So as a result, the Atari game, it can be a frame or RGB image of the game at the current time, right? So it becomes a matrix of pixels. In the game of Go, do you know what is game of Go? You know chess, right? Chess is a famous game. We also have some famous games in Asia. One of them is game of Go. We have some stones, black stones and white stones. I will explain it later in this lecture. But there are some dots or intersections, and we need to put these stones on the intersections, right? So it has some rules. It is a very famous game, I think, in East Asia. So in game of Go or chess, it can be a matrix, right? Why? How many cells do we have in chessboard? I don't remember. 8 by 8? Yeah, 8 by 8. So we have 8 times 8 number of cells, right? And each of which can have how many values can they have? A lot. Either empty or pawn or queen or king or elephant or these things, right? How many Yeah, we have a lot of things, right? So we can also reshape that to become a vector. So when we have a matrix, we can reshape it to become a vector, right? Having values for the cells of the board game. Anyways, so I gave you some examples of this state. Reward. The reward that the agents get when they play some actions. Better actions, of course, have more rewards. An example is this. In tic-tac-toe, when we have this, it's a reward because it wins the game, right? So let's move on. Now we need to talk about Markov decision process. Whenever we want to talk about RL, we should start with Markov decision process. But before Markov decision process, I need to talk about Markov process. Okay. Consider a time series. Have you passed any course on Markov models, hidden Markov models, discrete time Markov models, continuous time Markov models? Okay, I will explain it a bit here. So consider a time series. We have a time series. By the way, Markov was a scientist, was a mathematician, mostly working on time series, right? That's why you see Markov a lot in time series. Consider a time series of random variables, right? S1 to Sn. These are random variables. In general, so S1, then S2 comes, then S3 until Sn, right? In general, the joint probability of these random variables can be written as this. So this is a joint probability, right? Now let's use chain rule. Chain rule in probability. What is it? So probability of S1 times probability of S2 given S1. So because it's a time series, right? S1 comes, then S2 comes. Then probability of S3 given previous states. S3 given S2 and S1. Until, and so on, until probability of Sn given all of the previous ones. Sn minus 1, Sn minus 2 until S1, right? This is chain rule in probability. Chain rule or multiplication rule in probability. Now, what is Markov property? So Markov property is an assumption which states that in a time series of random variables, S1 to Sn, every random variable is merely dependent on the latest previous random variable and not the other ones. This is first order Markov property. What do I mean? So consider, so here, for example, here, consider this one. Probability of S3 given S2 and S1. What Markov says is that, do you agree that whenever I have S2, it kind of encapsulates the information of S1 in it? Because I already have conditional distribution of S2 given S1. So kind of some information of S1 is encapsulated in S2. As a result, Markov says, get rid of S1. You already have the information of S1 in S2. Kind of. It's kind of an approximation, right? So now extend it to other steps. It says that for every time step, only consider its previous time step, because the older ones are all somewhat encapsulated in terms of information in the previous one, right? This is first order Markov property. But we can have other orders too, such as second order Markov property. What does it say? Only condition on the previous two previous steps, the previous one and the one to the previous one, right? So the third previous one and before that, they are not important. They are already almost encapsulated in the two previous ones, right? So this is Markov property, okay? As you see, Markov property simplifies it, simplifies the process for us, right? By making some assumption. So first order Markov property, whenever we say Markov property, by default, we mean first order. Otherwise, we need to specify which order, okay? So Markov property says probability of S1 given the previous ones is equal to probability of S1 given only S minus 1, right? So as a result, with Markov property, the chain rule this chain rule is simplified to this. What happens? Probability of S1 times probability of S2 given S1 so far is the same, but this becomes simplified. Probability of S3 given S2 only. Until the end, probability of Sn given Sn minus 1 only. right? Did you see how simplified it become? The Markov property can be of any order. As I said, we can have second order Markov property. Usually the default one is the order of 1. Now a stochastic process, the time series of random variables, I mean. Whenever we say a stochastic, it means it is random. Deterministic, it means that it is not random. Okay. A stochastic process which has Markov property is called Markovian process or Markov process. Okay. Markov process. Let me briefly, very briefly, because we don't have enough time, briefly tell you what Markov model is. What is Markov model? So Markov model is kind of this model. So we have a bunch of models like this. Okay. What is hidden Markov model or HMM? In addition to this, we also have this. Okay. O1, O2, O3, O4. By the way, you know what I mean by this, right? It means that this is conditioned on the previous one, right? So in hidden Markov model, we have some states and some observations. Assume my eye is here. This is my eye. Looking to up, okay? What does my eye see? Only the observations, right? O1 to ON. These states are hidden behind them, right? Hence the name hidden Markov model, because we have some hidden states or latent states, okay? Why is this hidden Markov model very useful in machine learning, in statistical machine learning? Before, in ancient times, before the era of deep learning, whenever we had time series, we used to use hidden Markov model. For example, in action recognition, we have a time series of body poses or body states, right? For example, jogging, it is a time series of this state and this state, right? Or walking, this state and this state, or this action, this state, this state, this state, the time series of these. Then you can process it using hidden Markov model. And an interesting thing about hidden Markov model is that it is robust to repetition. When it is robust to a repetition, in other words, it is robust to speed. Because if I do it slowly, I have more states like this, maybe 3 states like this, then 3 states like this, then 3 states like this. But if I do it fast, 1, 1, 1. Right? So when I'm robust to repetitions, I'm robust to speed of action too. So it's very powerful, right? In other words, the probability of this doing it fast or slow is the same in hidden Markov model, right? Another use case of this is a speech recognition. In ancient times, nowadays they use deep learning. In ancient times, the year 2000, they use hidden Markov model because every part of a speech is a time series of phonemes. Phonemes are small parts of a speech, right? Okay. So this is Markov model. Now Markov decision process. Markov decision process, or MDP, I think it's obvious. It's a decision process because we said reinforcement learning is decision making, right? Which has a Markovian property. Okay, let's see. So it's a decision process which is Markov process 2. In other words, every state is conditioned on only the previous state in the MDP, where all the past information is assumed to be encapsulated in the previous state. Okay, so an MDP is defined as a tuple: state, action. So I have a state, action. By the way, these capital ones means it's a set. Okay, so I have a bunch of states, a bunch of actions, a set of actions, possible actions, right? This is the rewards. This is, I will tell you, this is the probability, transition probability, and this gamma is a discount factor. Let me tell you what these are. A state is a state. I already explained that. Situation of the environment. Action is what we do in that state, in any state, right? So we have some possible actions to do, right? Reward, we have reward belonging to the set of possible rewards that we have. We also have a reward model, which is probabilistic. What does it mean? Because we know that it's a stochastic process, it's Markov process, it's stochastic, right? So probability of the, so by the way, subscript T means the time, right? And RT means the reward at time T. ST means the state at time T, and AT is the action at time T. So given the state and action at time T, what is my reward? But this is probabilistic. It's not deterministic, right? Also, I have transition model in Markov decision process. What does it mean? Given my previous state and my previous action, what is the probability of my current action? How does my environment change based on my actions and my states, right? So this shows how my environment changes, how the states of my environment changes. And as you see, it's only conditioned on previous state. So it has first order Markovian property, right? Also, we have discount factor, gamma, which is between 0 and 1. So, of course, so assume the discounted rewards is this. R0 at current time, gamma R1, my reward in the next time step, plus gamma squared R2. As you see, as gamma is between 0 and 1, the more the power of gamma, the less it becomes. So as a result, gamma is to the power of 0, the largest, no discount. Then gamma squared, discounted more, right? Because gamma squared is less than gamma, right? Okay. So gamma is when gamma is less than 1, it is discounted. When gamma is equal to 1, then we know that 1 to the power of everything except something, I think infinity, it becomes 1, right? So note that the total reward is important, and I told you an example. So not short-term reward only. An example is, for example, let's sacrifice immediate reward to gain more long-term reward. Example is playing chess, where a player may sacrifice their queen to win the chess in 10 later moves, right? At every time slot T 0, 1, 2, right, etc., the agent is at state ST, of course. Okay. It takes an action AT, A standing for action, right? By this action, it moves to a new state ST plus 1. When you do some action, the state changes, right? You go to the state ST plus 1 according to this probability that we had. Do you remember? Probability of ST plus 1 given ST and AT. It was here. I think it's here. Yes. So if you, so ST given ST minus 1 and AT minus 1, you can see that ST plus 1 given ST and AT. Doesn't matter, right? Okay. It's a transition model. It receives our reward RT based on that, the other probability that we had, which was this, right? So we get some reward based on the state and the action that we have. Of course, we know that state is also important, because one action in some state might be good and might be bad in another action, right? In another state, right? So a state might be good in some, an action might be good in some state and might be bad in another state. So a policy pi, what is that? It's a mapping, you know, map in mathematics, right? Function is a special case of map, right? When we don't have to, if in function, we can't map one thing to two things. Am I right? Okay, so map or mapping from states to actions. What does it mean? Given some state, it maps it to some action. So it maps S to A. right? What is the difference of these two notations in mathematics? This is mapping, map. S is mapped to A. This means the map between the domains. Domains or sets, right? And these sets might be, for example, have you seen these? R2 to R. You know that the real space is a set, right? So there is a slight difference between these two. Okay. Anyways, so basically policy tells us what to do in every state, right? What to do in every, what action to choose in every state. And this policy can be deterministic, a deterministic function map, or it can be stochastic, probabilistic. So if it is probabilistic, then it is a conditional probability. Probability of AT given ST. Right? Correct? By the way, for this, I think we can use this notation too. What is this notation? It means sampling from this distribution. Yes.
Just one. So an MDP is a process in which the current state calculates or is basically the result of all previous steps it's done before.
So in MDP, we for finding the next state, we only consider the previous state and the previous action. We don't consider the next two previous states and two previous actions.
Yeah, like for example,
yes.
That basically encapsulates all the previous steps that you could have taken on that.
Yeah, so this is the assumption that Markovian process is saying that, for example, that Markov says that if you do a very awful action, then your state happens, some state happens, then it will have its impact in the next ones, because it will have its impact on this state, and this state for the next state you will condition on this state. So basically, Markov says approximately the previous information is encapsulated in only the latest previous state. This is what Markov process is saying. An example in real life: if you do a very awful thing in your youth, you might see its impact until age 40, just because every year is dependent on previous year, according to Markov first order, but the previous year also is dependent on this previous year, right? So it's like a domino, right? You don't need to condition on all previous years, only let's condition on the previous year, right? Am I right? Okay. The goal of MDP is to find a policy pi star which maximizes the long-term reward. So what is this? What is this notation? First off, what is this? Expectation. We know expected value, right? Expectation of the reward, because the reward can be random, right? It might be probabilistic. Expectation of the reward with respect to the policy pi, right? And gamma to the power of t, discounted, right? And t starts from 0. Why? Because of this. Do you remember? T starts from 0, and t starts from 0 to h. Assume we have a horizon from now until some horizon h. Okay. And so this is the whole accumulated rewards. And which policy maximizes that? As you see, it's not maximum of this. This is argmax of this. So its result is pi star, the best policy to do, right? Am I right? T is a time slot index, and H is the horizon, and this E is the expectation with respect to the policy, right? So Bellman's equation, one of the most famous equations, important equations in reinforcement learning. Bellman's equation. We haven't yet started reinforcement learning, but we are gonna soon. So value is defined to be the maximum or best reward that the agent can get in some state, right? What is value? Value is some important concept in reinforcement learning. Basically, it's just reward, another name for reward, but the best reward, right? So the best reward, because we might have different rewards, yeah. Yes, according to this, right? So maximum reward, as you see, it's not arg, it's maximum, because argmax, if you say argmax, its results would be action, because maximum is with respect to action, right? It's maximum. So the essence of value is the same as the essence of reward, right? So the value at st, state at time t, is the maximum reward. The reward itself is a function of a state at time t and action at time t, right? Which action at time t maximizes this reward? This is the value. As you see, value is not a function of at, because only one of the actions, one or several of the actions, will have the maximum reward in that state, right? So, by the way, the value at state t is denoted by various ways, VST or VTS, okay? In different literature, we have different notations. Anyway. Okay. So consider time period or horizon H. The last time slot of this horizon is at time t, and its value is this, okay? Consider a horizon from now until some horizon from now, okay? Consider the last step of this horizon. So now I'm deriving Bellman's equation for you. I'm justifying it for you. For deriving it, we need to come backwards, backward analysis. Okay? Yes. My reward, yes. But this is a final formula that we are going to talk about. But for the last step, it's this, yes. Okay? But I'm going to derive equation 8 for you. How? I will tell you. So assume this is time. So this is now, then go in the future until horizon, until the end of the horizon. At the end of the horizon, time t, my value becomes the maximum reward at that time, right? But now come one step back. What time slot? One time slot back. What happens? The value becomes the best reward in that time, but plus something, plus a discounted value in the next one. As you see, in the last time slot, there is no next time slot. So the value was the best reward in that time slot. But now when you come one time slot back, right? Then what happens? Your value becomes the best reward in that time slot and the discounted reward in the next time slot. Right? Discounted. So this is discounted. This is the this battery is died again. So this is the value in the next time slot, but with this probability. And this is the transition model, right? Probability of ST given ST minus 1 and AT minus 1. So this is the probability that I go to the state ST, and this is the value at the state ST. Agreed? We already calculated this here. Right? Now come to last time slot. Come to the last time slot. VST minus 2. Again, the best reward at that time slot plus discounted value in the next time slot with this transition probability, right? Now by induction, what do you get? This series can be generalized into the following equation. This is called Bellman's equation. What is it? The value is that value at state st at time t is the maximum reward in that state with respect to the action plus gamma, the discounted values. Why am I having summation st plus 1? Because from st, I might go to, it might be possible to go to several the other states, right? I need to sum over all of them. From this state, I might go there or there or there. How many possible st plus 1 do I have from this st? I need to sum over all of them. Agreed? So this is the summation and also the values. Agreed? Okay. This is called Bellman's equation. So by intuition, I just proved it to you. Yes. The probability of this probability, if you ignore this part, this becomes 1. But I have the value. Of course, summation of probability of st plus 1 given st and at would summation over st plus 1 is 1. But I have multiplication by value 2. Okay. So this is Bellman's equation that we found. I'm repeating it here. Again, Bellman was one scientist. Okay. So in the literature of reinforcement learning, the variable at the next time slot t plus 1 is also denoted by a prime. I know it's a bit weird. Sometimes when you read papers in reinforcement learning, sometimes they use t plus 1, sometimes they use prime. Prime means t plus 1. Okay. They sometimes for simplicity, they drop t and t plus 1. When they don't use prime means time t. When they use prime, it means next time, t plus 1, okay? So, for example, st and st plus 1 can be replaced by s and s prime, okay? Now, the value also may have superscript. Again, I believe in terms of notation, RL papers are a mess. When you move from one paper to another paper, the notations might change in a weird way. I don't know why they don't make a standard notation. So sometimes they use VS, sometimes they use V superscript S, superscript PS. When they use superscript, they means the value, but with the policy pi. Okay, with the policy pi at state S. Okay. Therefore, another notation for this equation. So you can write Bellman's equation in this way. So Vs equals maximum of R, S, and A. As you see, I have dropped this subscript T, but I don't use prime. Maximum with respect to A plus gamma, summation over S prime, which is ST plus 1. And this becomes this. Right? Okay. Sometimes this Bellman's equation is also written using expectation. So all of these are Bellman's equation in the literature. Expectation of, so Vs, they say, you can see this as expectation of the reward. So rather than maximum reward, they say expectation of reward given S, and sometimes they replace A with, you tell me, with policy S. Do you remember? What was policy? A map from a state to action. As a result, I can replace A with pi S. So they have replaced it with pi S. Right? And this expectation is with respect to the policy pi. And also here action is replaced by policy S and the rest as before. So several notations of the same equation. Okay. Now solving MDP. So what is the goal of MDP? Markov decision process. The goal of MDP is to find the optimal policy. What is the best policy to do at every state, right? Okay, this is the goal. There are two ways to solve the MDP problem, to find this best policy. These two are value iteration and policy iteration. Okay. So now I'm gonna explain value iteration in this slide. Let H denote the horizon that I can go, right? And T denote the time slot in the horizon. Okay. The algorithm of value iteration is this. First off, it calculates the optimal values backwards in the horizon, from the last time slot in the horizon until now, because Bellman's equation was like that. Its analysis was like that, right? So you say V0 star, which is the value in the last time slot of the horizon, is the maximum reward, right? By the way, the whole thing is inside another for loop for the states. Okay, because we might have several states, right? That's why I'm saying it for all S means that it is inside a loop itself. Okay, for all S. So for all of the states, you find their best actions. And then you go backwards in the time. So whenever I say T equals 1, it means that the 1 to the last of the horizon, right? T equals H means that a starting time of the horizon. So here, what am I using? You tell me. This is exactly Bellman's equations, right? You understand? Bellman's equation. And again, for all S. So it itself is in a loop over S states. And as you see, this gives me what? So at the end, I give VH star, the last VH that I have, as the best value. Okay, this is called value iteration. As you see, I'm iterating over the values. That's why we call it value iteration. Because the best policy will have the best value, right? The best policy will have the best reward, hence the best value. Okay, so I found the best value, and then after finding the optimal value by value iteration, how do we find the optimal policy, which is the goal of Markov decision process? How do we find it? Can be found for the last time slot and other time slots in the horizon. How do we do that? So for T equals 0, which is the last time slot in the horizon, I say argmax of the reward with respect to A. We know that max of reward is a value, but argmax is action, is the essence of action, right? And what is the essence of action? Policy. So do you agree with me that value and reward have the same essence? Policy and action have the same essence, because the output of policy is action. The input is a state, right? Agree? So that's why argmax of reward with respect to A is in the sense of policy or action. Gives me pi star S at time 0 for all S. And for T greater than 0, I use this, again, Bellman's equation. You see Bellman's equation a lot in reinforcement learning. Okay? And so I think I have missed some arc here. I apologize. Okay. The optimal policy pi star is non-stationary. That is, it is time dependent. You see that? According to these, they are not equal to each other. So when we say non-stationary, it means that it changes by time. Okay. Policy iteration. Another way to find the optimal policy in MDP is policy iteration. Okay. And what is that? I think its name is obvious. We iterate over the policy. So policy iteration alternates between two steps. It has two steps itself inside a loop. Okay, two steps inside the loop until convergence. These two steps are policy iteration and policy improvement. So this is policy. Sorry, this is. I apologize. I will correct these things in the slide. This is policy evaluation and policy improvement. So this is policy evaluation and this is policy improvement. By its name, it's obvious. First, assume you want to improve something, what do? Forget reinforcement learning. You want to improve something. You first evaluate it, see how good it is. If it is not good, let's improve it. If it is good, don't touch it. Right? This is exactly what policy iteration is doing. So it evaluates, then it improves it. Again, evaluates, improves it until it converges. So what do I mean? Policy evaluation evaluates how good the found policy is so far, and policy improvement improves the policy. Okay? This is the algorithm. So first off, initialize the policy with random action for every state. Because initially I don't have the policy. Let's have random policy. Okay? And then while not converged, while this value and the policy are still changing, not converge means that it is still changing a lot, right? So what do I do? First, as you see, again, I'm using in both of these steps, I'm using Bellman's equation. But one of them has arg in it, right? So this Bellman's equation, its output is in the essence of value, right? Arg Bellman's equation, arg max of Bellman's equation is in the essence of action or policy, right? As a result, the first one gives me the value. And why is it called policy evaluation? Because if the policy is good, the reward is good, so the value is good. If the value is large, means that the policy was good. Okay? And then which action maximizes this policy? This gives me the policy. So I do it repeatedly until I converge. These equations are both Bellman's equations, where in policy evaluation, the action A here is replaced by the policy S. You remember? So that's why it's called policy evaluation, because I'm using the policy for action inside it. Okay? If we want to compare the value iteration and the policy iteration, so the value in value iteration, the policy evaluation step is repeated. Do you remember? This is policy evaluation, the first step in policy iteration. We have this policy evaluation in value iteration too, here. Okay? So basically in value iteration, the policy evaluation step is repeated during the horizon to maximize the value. Okay? Then policy improvement step is performed only once. You remember? We do this policy evaluation a lot. Then we do this policy finding the best policy only once. But in policy iteration, we do this together iteratively. So we do them together inside the loop. Do you see that one of the differences is this? Okay. So in policy iteration, policy evaluation and improvement are repeated alternatively until convergence. Also, their complexity is different. Time complexity, without proof accepted from me, that the time complexity of every iteration in value iteration is we know, you know, big O notation, right? It's an upper bound complexity. S, the cardinality of S means that how many states do I have? How many possible states do I have? To the power 2, and how many actions do I have? Cardinality of A. This is for every iteration of value iteration. For every iteration of policy iteration, its time complexity is S cubed plus S squared times A. Which one is worse? Yeah, S cubed is worse. By the way, you don't need to raise hand. Interrupt me. Answer me. That's fine. So as a result, policy iteration in terms of every iteration is worse, right? I think it's obvious, but we have at least 2 things here. But in value iteration, we only have 1 thing inside the loop. Okay? So in every iteration of policy iteration is worse. But there is a but. Policy iteration usually converges sooner. So we have fewer number of iterations in policy iteration. But in value iteration, we need more number of iterations. Okay? Did you get it? So one of them has a lot of small iterations. One of them has a few large iterations. Okay. So they have pros and cons each, right? Let's have the best of 2 worlds. Let's have a middle case scenario. And that's called modified policy iteration. It is an interpolation case between value iteration and policy iteration. And what is that? It says that, do you remember the policy evaluation step which existed in both value iteration and policy iteration? Let's repeat it for k times. In the original policy iteration, it was only done once inside the while loop, right? Now we repeat it for k times, similar to what we had done in the value iteration. Do you see that? By the way, do you follow? Because you are very quiet. Do you follow what I'm saying? No? When did you get lost? Of course, you need to go and watch the video again and again for several times. But when did you get lost? Where? Tell me. No, tell me. Why are you shy? I'm your friend, right? Tell me that. I didn't understand this part. Explain again. Which part did you get lost? From? Okay, so until the end of this slide, did you understand or no? No? Okay, let me repeat from. Okay. Solving MDP. So, do you remember MDP, Markov decision process? So the goal is to find the best policy. You want to know what to do in every state, right? What is the best thing to do in every state? So we can find this best policy in 2 ways. Either value iteration or policy iteration. And what is their difference? In value iteration, we evaluate, we find the best values in the horizon, because we have a horizon, right? And in the horizon, we have the cumulative reward, right? From now until some horizon, what is my reward, right? Now in value iteration, I come backwards. From the end of the horizon, assume I'm playing chess. The end of my horizon can be when I win the end of the chess. You come from the end until now, right? So you come, 0 means the end of the horizon, H means the start of the horizon, right? I'm not introducing any new formula. This is Bellman's equation. This is Bellman's equation. Bellman's equation, let's go back to Bellman's equation. This or this or this, all of them are in the essence of value. You see that? Reward or value, right? Am I right? What is this? Best value. Reward, which action maximizes this reward? Yes. Yes, the value itself, the value you can see it as expected reward. So Bellman's equation is a formula for value in reinforcement learning Markov decision process. Okay, how do we find value or best reward in a Markov decision process? Bellman's equation says that. Okay, so Bellman's equation is in the essence of value or reward. Yes. H. So yeah, so we come from back at the end, from the end of the horizon until now. H, I believe H is a star. H is a star. Yes, I know this is confusing, but I didn't make this confusion. They made it. Okay. Yeah. They say this is a horizon, but T0 means the end of the horizon. This is backward. This is backward analysis. I didn't make it. Blame the inventors of RF. Okay. So, but did you understand this thing that Bellman's equation is in the sense of value? Now you tell me, rather than max, if I say argmax, Bellman's equation becomes in the essence of action or policy, because I'm maximizing with respect to action, right? Maximum of reward is a value or reward, is a sense of value, right? Argmax of value, argmax of reward with respect to action is in the sense of action or policy. Do we see the difference? So now in value iteration and policy iteration, I'm going to use these two types of Bellman's equations. One time I use its action, its value essence. One time I use its action essence or policy essence. One time max reward, one time argmax reward. Okay, so far clear? Yes. Yes. Whenever we see prime in reinforcement learning, means 3 plus 1. Yes, yes.
So we're saying the value of max of T plus 1.
No. So for example, when I mean, what is this? The best value at time T minus 1. Give me a second. So how should I say? When I come backwards in time, whenever I say S is this, S prime is this. Okay? Something like that. So S prime, whenever they use prime, they means one step ahead in the future. This is what they mean. Okay? Yes.
But one step in the future right now is one step back, right? Because H is.
I think this notation can be improved. I agree with you. Maybe if I change the notation from, I denote it by H, and then I say for T equals H minus 1 to 0, it becomes better. But at least for this one, I'm sure that S prime means the one time step in the future. Yeah. Okay. So try to understand the concept, but then I think mathematics is just Bellman's equation. Try to understand the concept. But prime, don't get confused. Although we are doing backward analysis, but prime means one step ahead in the future. Okay. At least for this, I think I'm confident. Okay. So where were we? I'm saying that now we have Bellman's equation in terms of in the essence of value and in the essence of action. So this equation is a Bellman's equation in the essence of value or reward. That's why, and I'm iterating in the horizon. So that's why it's called value iteration. Now assume I find all of the values, the best reward that I can get in the horizon. So I can, as a result, at the end, in one shot, I can find the best policies in the horizon, right? Which is argmax rather than max. This is value iteration. Policy iteration says that use the value essence of Bellman's equation and the reward essence and the action essence of Bellman's equation together and alternate between them. Okay, so use the value one, which is called policy evaluation, because we know that the larger the value, the better the policy. Then use the action essence of the Bellman's equation. This is called policy improvement because it's in the essence of action or policy, and alternate between them. Right? So again, a real world example, whenever you want to improve something, first you evaluate it, then you improve it. Again, you evaluate it, how good was it? Then you improve it until convergence, right? Right? Again, let me know if you didn't understand any part. Okay. And then here we compared them. Did you understand the compare? Yes. So I say that each of these have their own pros and cons. So one of them, the value iteration, in each iteration it is easy, but we have a lot of iterations until convergence. Policy iteration, every iteration has heavy computation, but we have fewer number of iterations. Okay, so none of them is the best. Both have their own pros and cons. As a result, someone said, let's have the best of the two worlds. Let's combine this. So this is the hybrid of policy iteration and value iteration. As you see, this part is kind of value iteration. But if you ignore the for loop, these two lines are policy iteration. So it's a hybrid, right? Yes. Give me a second. I think it's backwards. At least for value iteration, I'm sure that it is backwards. I read it somewhere. For policy iteration, I'm not sure. Do we have any person who knows RL better than me? No? Okay, I will search it and I will let you know in the next session. Okay. Sorry about that, that I'm not confident about whether it's backwards or forwards. I myself, when I studied RL, got confused about backward analysis too. But I apologize. When I started, I said that I'm not an expert. I think if Shriram was here, he would answer all of your questions better than me. But I'm not the best person for RL. At least I'm trying to let you know what I know about RL. So, but I will let you know. I will search offline and I will let you know. So we haven't yet started RL. Okay. So this was pre-processing for RL, for understanding RL. Now RL is the same as Markov decision process, except one thing. It doesn't have the transition model. Do you remember the transition model? What was it? P of ST given ST minus 1 and AT minus 1. Or the other way around. P of ST plus 1 given ST and AT. Doesn't matter. This was transition model. RL doesn't have this. So RL doesn't know what happens if I, in this state, if I do this action, what will be the next state, right? The next state will be unknown. As a result, RL, reinforcement learning, is more realistic, because in real world, we usually don't have this transition model, right? That's why RL is more powerful than Markov decision process for real world applications. Okay, so as you see, the other things are the same. Even the goal of RL is the same as goal of Markov decision process, which is finding the optimal policy. Okay. So there are two main approaches for finding the best policy in RL. Okay. Each of these approaches is evolved. There are surveys on them. Okay. You can write theses on each of these areas. So it's like a broad way in each of these. So one of them is model-based RL. The other one is model-free RL. What is the difference? So I have put surveys on each of them, reference 4 and reference 5. Okay. Model-based RL, it says it finds the model first. What do I mean by model? The transition model. That is not existing in RL, right? It finds the model first and then solves the problem. Basically, when you find the model, the reinforcement learning problem becomes a Markov decision process problem, right? And then it finds it. So specifically, it finds the transition model and reward model and then solves the problem. But model-free model, RL, it finds the policy without the transition model, without it, and the reward model. Okay. So in the model-free RL, the model is unknown explicitly, and it is implicitly found to solve the problem. Implicitly, I care about the model, not explicitly. Okay. In this lecture, we talk about model-free RL. Usually people, as far as I have seen, whenever they say RL, by default, they mean model-free RL. There are fewer researchers who are working on model-based RL. As far as I know, I might be wrong, but model-based RL, for example, one of the cases that I've heard is in, again, robotics and mechatronics, where you have an arm, for example, then they move the arm of the robot manually to different states and find out the transition model between the states. And then they solve the model. So they find the transition model by manually moving the robot's arm to different situations with different degrees of freedom. And then they solve the problem. But in model-free RL, they don't do these things. Okay? But as I said, usually when people are talking about RL in general, they are referring to model-free RL, as far as I know. Okay. So another important, so as I said, I'm focusing on model-free RL. Another important concept in reinforcement learning is temporal difference evaluation. Whatever I'm telling you is a very important concept, backbone of RL, okay? Temporal difference evaluation. What is that? First, let me talk about Monte Carlo evaluation. By the way, as you know, as so far you have understood, RL has a lot of probability in it, right? Conditional probability. That's why in many RL papers, you see the concepts in probability. So heavily in the literature of RL, you see probability, okay? One of the famous concepts in probability is Monte Carlo, okay? By the way, for more information on Monte Carlo and these things, read this paper of mine. So 25 pages about sampling algorithms from survey sample into Monte Carlo methods, tutorial and literature review. Let me tell you briefly what this means. So sampling can be divided into two broad categories. Sampling. either you have a set of values and you sample from these, right? Discrete values, you sample from them. Examples are simple random sampling. With replacement, simple random sampling without replacement, we saw them in high school, right? Or a stratified sampling, or cluster sampling. These are different sampling algorithms, okay? These are called survey sampling because they're very related to survey. For example, what is that word in English where they go and see how many people there are in the country and in each city and this? What? Census? Yeah, census. Census is a survey sampling method. They go to each house and they sample the houses, for example, and they count how many people are in this, and they can estimate based on this sample, right? So as you see, it's kind of discrete. This is called survey sampling. This is an area, big area in statistics. If you go to statistics department, some people are working on that, okay? Another area for sampling, so another category of sampling is Monte Carlo methods. What does it mean? You have a distribution and you want to sample from the distribution. All of them are called Monte Carlo methods. And there are a lot of ways to do that. So, for example, sampling from CDF, Monte Carlo approximation, Monte Carlo methods, such as Markov chain Monte Carlo, MCMC, right? And again, Metropolis algorithms. These are all methods for sampling from distribution. They are all called Monte Carlo methods. Metropolis algorithm, Metropolis Hastings algorithm. Who is Hastings? One of the most important statisticians / machine learning scientists in Stanford. Okay, Hastings, I guess, yes. He's in Stanford as far as I remember. Gibbs sampling, slice sampling. These are all Monte Carlo methods. Okay, for more information, read this paper. But why did I say that? We see a lot of Monte Carlo methods in reinforcement learning. We see Monte Carlo evaluation or approximation. What is that? So in the model free RL, the value should be estimated, right? When I don't have the model, I need to estimate the value, right? Given a policy pi, so I have the policy, assume. Now I want to estimate the value without any transition model, right? And the transition model would say, what state should I go from this state with this action? But I don't have it. So recall that value is the expected, do remember, value was the expected total rewards with respect to the policy, right? Value was a sense of reward, but the expected reward, expected discounted reward, right? So this is value. One way to approximate expectation is Monte Carlo approximation. What is that? So whenever you have expectation of X, you can approximate it by average. What is expectation? Another name for expectation. Expected value, another name for that? Mean. Whenever we say mean in science, means expected value. It doesn't mean average. Public people use these interchangeably, but they are different. Mean is different from average, okay? Although in programming languages, they use the same thing. So they mean, when they say mean, np.mean, numpy.mean, they mean average, but they are different in science, okay? Mean is expectation. Average is average, what we learn in high school, okay? When are they equal to each other? For some specific distributions. So mean means the mean of this distribution. So every distribution has several moments, right? Yeah, moments. So expectation of X is first moment. Expectation of X squared is second moment. Expectation of X cubed, third moment, until infinite moments, okay? And each of, so this is mean. This is related to both mean and variance. Recall preliminaries. I think I talked about it in the preliminaries. So variance is related to both expectation of x squared and expectation of x. Also, this is related to skewness. What do I mean? Whether it's like this or it's like this. So each moment is showing some characteristic of the distribution, right? Now, for some distributions, the mean becomes average. Okay, one of them is Gaussian distribution. And that's why now you understand why public people assume that mean is average, because Gaussian distribution is the most common distribution in the world, most common continuous distribution in the world. That's why people think that mean is average. Okay, now Monte Carlo approximation says approximate mean with average, but when you have a bunch of samples. So expectation of x is expectation of x distribution of x, but assume you have a bunch of samples from this distribution. Okay, so n samples. Then I say yes, give me a second to remember. Yes, I think it was like this. Okay, and now this is called Monte Carlo approximation, also called Monte Carlo evaluation. So what about f of x, expectation of f of x? F is a function on the random variable. Then this approximation becomes 1 over n summation of f of xi. I goes from 1 to n. By the way, there are some different, I have seen these different denoting things or notations in different departments, because I have passed different courses in different departments. Each department has its own language. For example, in engineering, we say n samples, but when you say this in front of a professor in the statistics, they will laugh at you. They call it a sample of size n. They call it one sample of size n. But in engineering, we say n samples. Okay. Anyways, so a sample of size n or n samples, we have this, right? And then we approximate it in this way. So as a result, this is a function of RT, right? So I can approximate it by this average. And this summation is the summation of average. This summation is the summation of function. Okay? Did you get it? Of course, this n in the Monte Carlo approximation, the larger the n, the more accurate this approximation is, right? So it's a trade-off. Okay. And what is this ns? This ns is the number of times that the state S happens. How many times the state S happens? Because you are interacting with the environment. Once you see this state, maybe in 10 iterations, you see this state again. So ns becomes 2. Then ns becomes 3, right? RTK is a reward at time t in the horizon and the kth episode. What is episode? Because in reinforcement learning, you interact with the environment, right? And you usually play some game. Whenever you play the game from the start to end once, it's called one episode. Assume you are playing chess. You play chess once, at the end you either win or lose or draw, right? This is one episode. You do it again. So for training RL, you need to play again and again, right? So these are called episodes. And you can see that we have a lot of episodes. In the kth episode, at its time t, RTK is the reward at time t in the kth episode. Okay? So far clear? So the larger the NS, the more accurate the Monte Carlo approximation is. Right? Okay. Note that value is at a state S. So for every S, NS is different. Right? Agreed? For this Monte Carlo evaluation of the value, the agent should play the environment for k times, as I said. An episode is referred to each time that the agent plays the environment once completely. Okay. So consider this example. In the following game, this is a game. So yes. No. So let me tell you in this way. Do you remember I said for Monte Carlo approximation, we need a sample of size n or n samples, depending on which department we are in, okay? Yeah. N samples. In reinforcement learning, for Monte Carlo approximation, we need n episodes. So as you see, k goes from 1 to ns. Okay. So in other words, the more we play, the better the approximation becomes. Of course, I think it's intuitive, right? Okay. So for example, in the following game, the possible actions at every middle node. So consider this game, whatever we call it, game, environment, whatever. So assume I start from this node D, then what are these? The possible actions going right or left. And these are stochastic actions, right? These are probabilistic actions. These are not deterministic. And on these nodes, in the middle nodes, the reward is 0. At the end, node G has reward +1. Node A has reward -1. So what does it mean? I want my agent to learn to go to right. Going to left will lose the game. Okay? This is a simple game. Then what happens? So the policy is a stochastic, which is left or right movements. Policy is stochastic, right? And with different probabilities on the nodes. Okay? For a particular policy, particular probabilities of actions on nodes, the game is played for k episodes. We play it for k episodes, for k times. Every episode is represented as a trajectory ending either on node A or node G. Of course, when we reach node A or G, the game ends, right? Right? The Monte Carlo evaluation is the average of total rewards across the trajectories, right? So these words that I'm using, I'm not making them up. These words are used in the literature of RL. Sometimes rather than episode, they say trajectory, because you can see it as a trajectory of states. Okay? So far clear? Now temporal difference evaluation. The problem with the Monte Carlo evaluation, there is a problem with Monte Carlo evaluation. What is that? You need to play again and again. N should be large for the approximation to be accurate. That's a pain in the neck. That's a problem, right? So it needs many iterations. A large NS to be accurate. For addressing this problem, the temporal difference was introduced. Okay? So what is it? Let GK be the one trajectory Monte Carlo evaluation of the value. What do I mean? What do I mean? Do you remember Monte Carlo evaluation? 1 over NS summation, this. So if NS equals 1, then I will only have this. In other words, expectation of X was replaced with X. Okay? Expectation of F of X was replaced with F of X. Only one trajectory, one sample. Okay? I define it as G. In other words, G is a total discounted reward. Do you remember? This is total discounted reward, right? It seems that you have lost. Where did you get lost? Which slide? Let me finish temporal difference and we'll have break. But which part did you get lost? From here? So until the start of this slide, did you all understand? Don't be shy. Okay, so now I'm saying that Monte Carlo approximate. You didn't understand which part? Which part? Okay, so I'm saying that do you accept this from me or not? This is approximating mean with average. Okay, assuming that the distribution is Gaussian. Even if the distribution is not Gaussian, we can approximate it. Do you know why this approximation is very common and useful? You might be wondering why this. For several reasons. First, let me tell you. First off, the Gaussian distribution, in the Gaussian distribution and several other distributions, the mean is the average. And we know that the Gaussian distribution is the most common distribution, most common continuous distribution in the world. Even we have Gaussian filters in our eyes. So in nature, we have a lot of Gaussian distributions, okay? Also, have you heard of central limit theorem? What does it say? It says, consider a bunch of data points, add them up. The distribution of this addition becomes Gaussian distribution. It's very interesting, regardless of what distribution they have. When you add them up, the distribution of this addition becomes Gaussian. And of course, if you have the more samples you have, the more accurate this becomes, the more Gaussian it becomes, okay? And it's interesting is that in physics, we have a lot of addition. In the real world, we have a lot of additions, right? We have a lot of additions in this world. When the lights, the color that I'm seeing is the addition of several lights. See, so we have a lot of, that's why in nature we see Gaussian distribution a lot, according to the central limit theory. Okay, so because there's, yeah, we don't know the expectation of X, right? Expectation of F. So now this is the approximation called Monte Carlo approximation. The reason they call it Monte Carlo, I have explained it in my survey that I showed you in the paper. It was a secret project some time ago. I don't remember, in the previous century. That's I think in some area named Monte Carlo. So they named that project Monte Carlo, and then that it remained in the literature of probability. So they call these things Monte Carlo. Okay. Anyways, we don't care about the name. We can call it Bellman evaluation. So Monte Carlo evaluation or approximation approximates it in this way. Okay. Now expectation of f of x can be approximated by the average of f of x. And this, now let x be RT. So f of x becomes this summation. Okay. Now I approximate it by this. This summation, the first summation is the summation in the approximation. The second summation is the summation in the function. Okay. So now for this, so I have n samples, right? In RL, I need to do it, repeat it for several times. I need to repeat the game for several times. Okay. Of course, the more you play, the more you will see the state. So the NS will be larger. As a result, the approximation becomes more accurate. And then I gave you some example of a game where these are the rewards on the nodes. I have +1 here, -1 reward here. I start from here. So if and this is a stochastic, so I might be like this. I don't know. I might go like this. So if I go like this, I lose. So if I go to the right, I will win. Then if we apply RL to this, it will learn to go right. The policy will be good. So the probability of going right will be larger because we are updating the policy, right? Now, one problem exists in Monte Carlo approximation, and that is for the Monte Carlo approximation to be more accurate, the sample size should be larger, right? N should be larger, NS should be larger. As a result, this is a pain in the neck You need to play the game a lot and a lot. So they are introducing something named temporal difference. And what is that? I'm explaining temporal difference in this slide. First, consider GK. I did define it to be total discounted reward. Okay. So far clear? Okay, now let's continue. According to equation 12, this was the Monte Carlo approximation, right? Right? Then, do you agree that I can write this summation as GNS, the last one, plus the first one to the one to the last one? Right? So far clear? Shout at me if you don't understand any part, okay? Don't be shy. And don't think that it is hard for you. It's hard for everyone. It's hard for me too, okay? Don't be shy. So then, what can I do? So consider this equation again, but for ns minus 1. As a result, I can replace it with this. Because v ns minus 1 is 1 over n minus, so because of this, v ns minus 1 is 1 over ns minus 1, this summation of gk, k from 1 to ns minus 1. Right? So far clear? So now I simplify this. Basically, this ns and this ns become simplified. So I will get v ns minus 1 s and 1 over ns, the other terms. Right? Right? What happened? Interestingly, vns became vns minus 1 plus some other thing. This is called temporal difference. So this is the difference or temporal difference between vns and vns minus 1. Right? Right? So as a result, this is incremental update. So by this, I'm having an incremental update from vn minus 1 to vn, right? By the way, in the literature, again, I said that the notation of RL is a mess. Rather than ns, sometimes they use n, okay? So they simplify notation, and then rather than 1 over ns, they replace it by alpha n. So they generalize it. They say alpha n can be 1 over n or some other function of n, okay? And it has some conditions on it. I will tell you. Just bear with me. And the rest is as before, okay? So far clear? So where were we? This is what we found. Now the temporal difference evaluation is similar to the incremental update, which we had here, except that it replaces gn. This gn is replaced with r plus gamma vn minus 1 s prime. What was gn? Was the total discounted rewards, right? So they are replacing gn with reward plus gamma vn minus 1 s prime, discounted values in the previous one, if we n minus 1 s prime in the next one. Sorry. So as you see, this makes sense. This replacement makes sense because both are in terms of reward. gn is in terms of reward. This is also in terms of reward, right? Right. So now I'm replacing this gn. Guys, why are you laughing? Let me know if there is any ambiguity, okay? So I'm replacing gn with this, which makes sense, right? This is called temporal difference, okay? This replacement makes sense because according to equation 13, gn was value total rewards, right? Recall Bellman's equation. Again, TC, Bellman's equation is used a lot in reinforcement learning. Gn is a Monte Carlo evaluation of the value only using one trajectory, right? So this was Bellman's equation, right? I replaced this with only one r, and I only consider one s prime. So it's a simplified in this term is a simplified Bellman's equation for reward. Okay. Do you remember I said alpha n? It can be 1 over n or some function of n. It cannot be any function of n. It needs to satisfy some n. Of course, 1 over n goes down, I think, like this, right? Of course, it needs to be decreasing. So if alpha n, there is a theorem, and these theorems have their own proofs, okay? If alpha n is appropriately decreased with the number of times a state is visited, right? ns was the number of times a state is visited, or n is the number of times a state is visited. Then Vn pi s converges to the correct value. In other words, alpha n should be decreasing in terms of n good enough, okay? So it needs to satisfy these two. There are sufficient conditions for alpha n. What do I mean by sufficient? As long as I satisfy these two, I'm good. Okay? So limit of summation of alpha n, n goes from 1 to k, k goes to infinity. In other words, add alpha n, alpha 1 plus alpha 2 plus alpha 3 until alpha infinity. They should become infinite. Of course, it does. It happens for all 1 over n. 1 plus 1 over 2 plus 1 over 3, etc. It goes to infinity. But when you cube them, when you square them, the summation will not go to infinity. Okay? I guess this doesn't go to infinity. You can verify it by calculus that you have passed. So alpha n is called the learning rate. Okay, it's called the learning rate. Why? Do you remember in gradient descent, for example, we have learning rate, right? We saw that learning rate also in meteoristic optimization. So learning rate, and it can be any function of n satisfying the above sufficient conditions. For example, 1 over n is used a lot. Mostly 1 over n is used for alpha n. Okay. So instead of trying to calculate total future reward, temporal difference simply tries to predict the combination of immediate reward and its own reward prediction at the next moment in time. Okay, because this is a difference between Vs, Vns, and Vn minus s. This is a difference, right? This is what temporal difference is. And let me tell you the intuition behind temporal difference by some example. For example, consider this. Consider weather prediction. Okay. Assume, so I want to predict the temperature of days in the coming week, right? When one of the days of the week arrives, the predicted temperature of that day can be compared with the actual temperature of that day. For example, assume that the predicted temperature of Tuesday was 19 and the actual temperatures of Monday and Tuesday were 20 and 23. What do I mean? Assume I predict Monday, Tuesday, Wednesday, etc. Right? Assume I predict, you tell me. Assume I'm in Monday. In Monday, I'm actually 20 degrees. I predict it to be 19 tomorrow. Okay. Now I wait a day and tomorrow arrives, Tuesday, it's Tuesday, and I see it's 23. So I have made a mistake in my prediction. Okay. Now I correct or I adjust my predictions for the next days using this error. So what was that? So basically, I will say that it was 20 plus my adjustment becomes this alpha times 23, my actual Tuesday, minus 19, my predicted Tuesday. Do you see that? And this alpha is a learning rate. And I can use this adjustment for the future days as well. If my error today was small, apparently my future predictions are still correct. But if this error is large, I need to adjust my future predictions for Wednesday, Thursday, Friday. Do you see what temporal difference is doing? Okay, so when the next moment comes, the new prediction is compared against what it was expected to be. In other words, the temporal difference is calculated. So this is the algorithm of temporal difference evaluation. So by the way, this is temporal difference evaluation of value. Do you remember when we started this temporal difference section? I said we don't have the model in reinforcement learning, so we need to estimate the value. We use this temporal difference to estimate the value. So what do? Input some policy pi. Okay, initially the policy is random, right? Input some policy pi, while this value of this policy is not converged because we are changing the value inside this while loop. Okay, then execute this policy on the state S. Okay, so when you execute the policy, it means that it gives you the action, right? The output of policy is action. Its input is state, its output is action. Then observe, you already knew what state you were in, but by that action, you will also see the next state. So you know S and S prime both, right? You are in some state, S. You do some action by policy pi S, you will have the next state S prime. Okay? As a result, you also increment NS because you saw the state S once, right? By the way, NS is initialized by 0, right? Then alpha becomes 1 over NS. You remember? Alpha, the most common formula for alpha N was 1 over N. Then you use the temporal difference that we talked about for updating the value. Right? Recall that temporal difference was in the essence of value. Always notice the essences of formulas in reinforcement learning, not to be confused. The essence is either in terms of value or reward or action or policy. Okay. Okay. So then you go to the next state and you do this precision again until your value doesn't change a lot. In other words, it converges. Sorry. Right? So this means that go to the next state. S prime, let it be the S again. Right? At the end, return the converged value for this policy. Right? Right? Note that the input was policy, the output is the value for this policy. Did you see that? Did I use the model, the transition model here? No, because I don't have a transition model in reinforcement learning, which is a realistic scenario, right? But I could say that, okay, I'm dealing with some environment by the state and doing the actions based on some policy, I could find out the value. So basically, I could evaluate my policy. If this value is large, it means that my policy is good. If this value is small, it means that my policy is awful. Right? Because value is reward. It's very cool. By interacting with the environment, I could find out whether the policy is good or not for this environment. Yes. It's not changing the policy. Policy is the input. So you can change your policy and you run this algorithm again to see how good this policy is. It estimates the value for this policy. It estimates the value for this policy without transition model. Very cool. It's like a miracle, right? So as a temporal difference at evaluation of value is making use of incremental updates, it has much less computation compared to Monte Carlo evaluation of value. Do you remember? We can estimate the value by Monte Carlo evaluation, but we need to run the algorithm a lot. But temporal difference doesn't need that. Right? Very cool. The Monte Carlo requires to calculate the total trajectories, but temporal difference only calculates the differences of values of successive states along the trajectory. Cool. Okay, let's have a break. The class is until 9:20, right? Okay. Can we come back at 10 to 9, or you want to have a full break? Raise of hand 10 to 9 is fine. The total break, raise of hand.
No break, let's just.
Many of you don't.
Yeah, or just use it. Yeah, just.
What?
Like. Going to
So raise of hand not having a break and continuing. Yeah. Apparently this has more votes. Okay, let's continue. Okay. So Q function, instead of, by the way, Q function is the next important topic in reinforcement learning. As you see, by the way, if you leave, you will not understand them. Okay. Because every part is dependent on previous part. Okay. So Q function is another important function in reinforcement learning. So instead of evaluating the state value V pi s in the previous slides, we estimated the value, right? Now it is possible to evaluate the state action value. So another thing which is in the essence of value. So far, we saw two things which were in the essence of reward. One of them was reward, one of them was value. Now I'm adding a third thing, which is Q function. Q function is also in the essence of value or reward. Okay, how is it different from value? Value, its input is a state. Q function, its input is both a state and action. Okay. Value says that for this state, do the best action that you can do to get the best reward. That is value. Q doesn't say the best action. For this state, for this action, what is my reward? Okay. This is called Q function. The state, so this is called a state action value, also called Q function. Okay. So the state value shows how good it is to be in a particular state S, right? With the best action. But the Q function determines how good it is to perform action A by policy pi in the state S. Right? I don't know why they call it Q function. Do you know that? There must be a reason, but I don't know the philosophy behind that. Okay. Recall the Bellman's equation. Again, everything goes back to Bellman's equation. Bellman's equation for the state value V. Do you remember this? We also have Bellman's equation for Q function. So this was Bellman's equation for value, a state value. We also have Bellman's equation for a state action value. It's this. Compare these two. So basically this has been replaced by this because we know that here shouldn't be dependent on the action. As a result, we have maximum of Q with respect to A prime, the next action, right? And also V is replaced by Q, right? A prime is the next action in the next time slot. A is the action in this time slot. Okay. As a result, Bellman's equation, according to Bellman's equation, the optimal state value and the optimal Q function are these two. So this is a star means the optimal best. So basically, if you consider this, it's optimal. I'm using stars here. For Q, it's optimal. I'm using stars here. Right? Okay. Now, if Q function is used, then the optimal value V star and the optimal policy pi star is found by maximizing the Q function. What do I mean? Do you remember? So assume we have Q function. Assume we have Q function, which is S and A, right? A function of state and action, right? Now assume I have the optimal Q function, which is Q star. Okay. I want to find the optimal state value function, which is V star S. How can I do that? I should get rid of this action, right? So I should basically say which action maximizes this Q star. I use max, not argmax. Why? Because argmax will give me action, but max gives me reward and Q. We know that Q, value, V, and reward R, they are all in the same essence, right? Argmax of this gives me the best action or the best policy, because policy and action have the same essence, right? Also in physics, when you want to learn equations, you should notice the essences of the sides of the equation. In reinforcement learning, you should also notice the essences, right? For example, in physics, if this side is kilogram per second, the left side should also be kilograms per second, right? So maximizing the Q function for finding the optimal policy is roughly in the form of equation 7. So assume this, what is this? Total discounted reward, right? Which policy maximizes this? It can also give me pi star, right? Argmax, which found the policy by maximizing the value or the total rewards. Okay. Now recall equation 15, which was the incremental update. Do you remember incremental update for value V? We also have incremental update for Q function. So whatever we have for value, we have it for value Q2. Okay, so this is what we found in the previous slides. Likewise, we have it for Q. How is it different? This has been replaced by this by this, and this by this. It's basically the same equation, right? And Gn is defined as before. As before. Okay. As a result, the policy iteration algorithm, recall policy iteration algorithm with value. We saw it, right? Now we can also have policy iteration algorithm with Q function. Using Q function. So it's basically the same, very similar to before, but here, so here this is policy evaluation, and this is policy update, right? But also I'm using temporal difference for policy evaluation using Q function, right? I'm using temporal difference. So far clear? Is there anything which was unclear to you? So why are you looking at me like this? Which part did you get lost? Which part, no really, which part did you get lost? Tell me. Which slide? How much should I go back? So from here, I said that we have value V. Let's replace it with Q. And how is it different? Value is a function of S with the best action possible to do in that state S. Q is a function of both S and action. And they are both in the essence of value or reward. Yes. So if you will, it gives you different algorithms, but if you want to find the best value for all possible actions, then you use V. But if you care about values of different actions, rewards of different actions, then you need to use Q function. Because you remember for value S, it was defined as Bellman's equation, maximum of reward with respect to action, right? But here, Q is a function of both state and action. And now basically I'm repeating whatever we had for value for Q. So I'm Bellman's equation, this also temporal difference. I'm just redefining them for Q function. Do you remember we had policy iteration using V value, V? We had it in a few slides ago. We can also use policy iteration for using Q function, right? So here for this is policy evaluation, this is policy update. So I'm replacing policy evaluation with this, where I'm using temporal difference for Q. Do you agree that the larger the Q, the larger the reward, the better the policy? Do you agree? Right? So I defined Q function. Now Q learning, another concept in reinforcement learning. By the way, you might be angry at me right now, but you will be thankful to me in a few years. Okay. I'm teaching to you, I'm teaching, I think, 4 courses to you in this course. Okay. And I'm not evaluating very hard, right? Because the purpose of learning is just learning with joy. And you will see the fruits of this in a few years. Okay. Q learning. And you know that at the end, I will curve the grades. So you don't get worried about the grades much, but you will do your best, right? You will do your best. So Q learning, recall that equation 16, which approximated the Monte Carlo evaluation of the value using one trajectory. Do you remember? So this was Bellman's equation, and I said if we replace this with only one value, well, one sample of Monte Carlo approximation, so expectation of reward becomes reward because it's one sample. And this, I assume I only have one next state. So the summation goes away, and this probability becomes 1, and I will have only 5 pi s prime. Okay? Okay? Then what happens? Likewise, I can have approximation for the Q function here. So this was the Bellman's equation for Q function. Again, using one sample in Monte Carlo approximation, it becomes R, and this is simplified to only this part. Only this. Right? Okay. As a result, the temporal difference evaluation of Q function is this. So, do you remember? Just give me a second. Where was that? So, what was this here? We had Gn minus 1 pi Q n minus 1 pi SA. Oh, sorry. Here, Gn, do you remember that? Gn. This is Gn exactly. This is Gn. This is Gn. So I can replace Gn with this in the temporal difference. Because Gn was a total discounted reward, which was approximating the Monte Carlo approximation with only one sample. Okay. Basically, expectation of f of x, replacing it with f of x. Get rid of expectation. Okay. Now I have this. So it is similar to the temporal difference for a state value in equation 17 that we had. So now we are going to use this. It is noteworthy that Q function is updated merely by observing S, S prime, A, and R. Can you see this? Let's analyze this equation. 27. So what is it? It's updating Q function, right? Based on the previous Q function, right? It's updating the Q function. Well, how is it updating that? It is using S, A, S prime, A prime, right? Right? So what is S? Current state. S prime, next state. A, current action. R, current reward. Only using these four things, I'm updating the Q function. And Q function tells me how good the policy is. It's a miracle. It's a mathematical miracle. Okay. It's very good. So this, based on the temporal difference, this leads to Q learning algorithm in the following. Okay. It is also worth comparing the updates in Q learning and value iteration. Do you remember this was in value iteration? Compare these. Compare these. Value iteration for MDP, right? But Q learning is for RL. Interesting. Do you remember value iteration that we had? It was for Markov decision process, where we have the transition model. Here, Q learning is for reinforcement learning, where we don't have the transition model. Interesting. In MDP, the transition model is known, but RL doesn't have. Therefore, RL updates the Q function, which depends on both state and action. Now, do you see the philosophy of why? I think answering your question, why we also need Q function here? Because we don't have a transition model, and the Q function depends on both the state and action. But in Markov decision process, we don't need Q function. We have the transition model. We know using in this state, by this action, which state I go to. But in RL, I don't know them. Okay. This is Q learning in reinforcement learning. While Q star, so Q star is the optimal Q, right? Not converged, which means that changes a lot. Select and execute some action, A, right? Observe the next state S prime and the reward, current reward, R. Then, now my N becomes N of, not just N of S. N of S and A. Number of times that, you tell me, what does it mean? N of S and A? Number of times that I see state S and action A together. In this state, I do this action. How many times this happens? Okay? Do you see that? The number of times we see them together. So we increment them, and then alpha becomes 1 over NSA, right? And I use this temporal difference of Q to update my Q, right? Right? So, and then I go to the next state. I think it's obvious what it is doing. So I have some formula for updating Q. See, forget mathematics. Assume Q is Benjamin. Ben equals Ben plus some delta. So I have a for loop on that. What does it mean? I repeat this until delta becomes small. Initially, delta is large. So then delta is, you calculate delta in every iteration, right? Initially, delta is large. This is the delta, the temporal difference. Then gradually this delta becomes smaller and smaller until the previous Ben is almost the same as the new Ben. So you convert. The Ben has converged. Now replace Ben with Q. Right? Yes. So it's, of course, you will have some policy, I believe, as input. For some policy, sorry, give me a second to think. Yes, as you see, for this policy, this is my Q. Again, input is policy. You might say, why is it useful? Why is this algorithm useful? It tells you how much this policy is good, right? The larger the queue, the better the policy, because the larger the queue, the larger the reward, the better the policy. So it kind of is evaluating the policy, right? So using S prime, A, and R, you will find out how good the policy is without having the transition model in the environment. It's a miracle. So there are two approaches for selecting action A. Answering your question, either choose the action A at the state S randomly, or choose action A, which maximizes the Q function. Okay, but again, it depends on the policy as well. But this goes back to exploration and exploitation that we had. Okay, that we had in meta-heuristic optimization. Assume I execute my actions randomly. What happens? In other words, my policy is random. What happens? I will converge very late, right? But I will explore what I can do, right? So I have exploration, but I don't have exploitation. Now assume I find the best action at every state, which maximizes my reward. Then what happens? I will converge very soon, but I might get stuck in a local best. Do you remember meta-heuristic optimization? So in that case, I will have exploitation, not exploration. So what should we do? Let's have a middle case scenario, a combination of them, right? For example, we can start with exploration and gradually decrease exploration and increase exploitation, exactly how we did it in meta-heuristic optimization, right? Because initially, I want to explore. Initially, I'm young. I want to explore my possibilities. Gradually, I get old. I'm getting closer to my solution. I'm supposed to get closer to my solution, right? So I shouldn't explore a lot. They shouldn't oscillate around my solution a lot. So this is what we do. Okay, a combination of them. Exploration and exploitation. Okay. Now consider this example. So this is Q learning. Example for Q learning. Assume the current Q function at this iteration for the states and actions are this. Assume it's this. So what do I mean? Q has both a state and action as inputs, right? At a state D, action going right, let it be 16. Okay, Q function is so it has inputs and outputs is 16. Q for D going to left is 10. I think makes sense. Why? Because going right is better in this game, right? Going left will lose. Going right will probably win. Q for state E action going right is 20. Q at state E action going left is 15. Again, it makes sense because going right is better, right? Assume I said that. Now assume that at the current iteration of Q learning, we are at the state D and we choose action moving to right. Assume. Okay. So the next state is E. Agreed? If you are here, we go right, we go to state E. So S is D, S prime is E. Agreed? What is action? Action is right, going right. What is reward? Reward is 0 at this state, right? Then assume N, D, and right, the number of times that I went right at the state D so far is 2. Okay, N, S, and A is 2. Okay, so far. And let the discount factor gamma be 0.9. Discount factor should be close to 1. Shouldn't be. If discount factor is 1, I don't discount anything, right? I consider everything with equal weight in the horizon. If discount factor is 0, I only consider my current reward. I don't care about my horizon. So gamma should be close to 1 because I want to consider the horizon. So 0.9 is fine. In this iteration, by performing this action at this state, QD right gets updated. How? So previous QD right equals, current QD right equals previous QD right plus some temporal difference, right? According to that equation. Alpha n is what you tell me. So what is my previous QD right? 16. What is alpha n? Is 1 over nd right, 1 over 2, half, okay? What is, you tell me. So what is R? So this is the formula. What is reward? Reward is 0 at this state, D. Gamma is 0.9 times, what is this? What is Q star, E, and A prime? You tell me. What is A prime? We are maximizing with respect to A prime. What next action at a state E will maximize its Q? So I have two options. Either I go right or left. Right is 20. Going left is 15. Maximum of them is 20. Right? Did you understand? So here I have two possible actions. If I had 3, I need to take maximum between 3 things, right? And then minus this, what is this? QD and right, previous one, which was 16. So basically it becomes 16 plus half times this 0 goes away. 0.9 times 20 minus 16, it becomes 70. 17. 17, okay? And interestingly, it got updated from 16 to 17. Does it make sense? Yes, because we went right. Indeed, we went right, so it should be rewarded. If we had gone left, Q would decrease. Do you see the beauty? Did I have transition model? No, I didn't have probability of E given D and right. Otherwise, it would be Markov decision process. Interesting. This is a miracle that I'm talking about. Okay. So, Q function approximation. The Q function can be approximated by a linear or nonlinear function. Now I want to approximate my Q function. Okay? Okay. Let me say this. Q function. Now this I need to approximate it by some function, and this function can be linear or non-linear. Agreed? Agreed? Yes. So, for example, it can be approximated by a neural network. Do you agree that neural network can be a function which approximates something? And it's a nonlinear activation function, nonlinear function, because I have nonlinear activation functions in the middle of neural network. Okay. So it is nonlinear function. Let Q, W, S, and A be the approximated Q function. Okay. With parameters W. What are the parameters of neural network? The weights of neural network. Right? By the way, I'm stepping out to reach deep Q learning, deep Q network, DQN. Okay. So I can approximate it by a neural network with weights W. Right? Then, do you remember this temporal difference for update of Q? Right? So, what is this doing? It is the temporal difference between this term and this term. So this term and this term. This is a temporal difference, right? Now, what should we do in neural network? In neural network, we need a loss function. What is the ideal case for convergence? That these two become equal to each other. So this delta, this difference becomes 0, right? Do you recall Ben equals Ben plus delta. Delta needs to become small. So let's use mean squared error between these two terms as a loss function. This is this, and this is this. This minus this. We are in the head of people in DeepMind before joining Google. DeepMind, it wasn't in Google yet. At that time, they were designing this. It was a simple company. They had a brilliant idea. They implemented that. Google bought them. I think for millions of dollars. Okay. It's very interesting. They said, let's use this as a loss function. So then I optimize my W. So I optimize this loss function, my neural network, by back propagation to minimize this. But there is a problem. Nothing is easy in machine learning. So there is a problem. What is this? When you change W, both this and this change. You want to modify this, right? This is my I want this to be similar. So let it say 1 and 2. I want to tune my parameters W, weights of neural networks, so 1 becomes similar to 2. But when I change it, both 1 and 2 change. Let's call 2 targets, which I want to become similar to. My target changes when I change my weights. As a result, I have a problem of moving targets. Assume I wanna catch someone. I wanna become close to someone. But when I reach to that person also goes away. I'm coming to you, but you also go away. I never reach you. So the target is moving, moving target. Okay, so it might not converge because it becomes like a hide and seek. If you go away from me, right? So I have a problem of moving target. It has been empirically observed that, empirically by experience, if Q function is linear, minimizing this loss function converges. But if it is non-linear, it may not converge. And neural network is a non-linear function, right? So what do? There are 2 approaches. We have 4 more minutes. Let me say this because this is important. There are 2 approaches to resolve this problem of moving target. Okay? One of them is that, so we know that the Q function in the target can be fixed. Let it be fixed. So let's fix the target. Don't change it. And only change 1. Don't change 2. Fix it. As a result, I'm using W bar for it and W. So in other words, I use 2 networks, 2 neural networks with the weights W and W bar. So I have target network and Q network. I want to update this only. Okay. Have you heard of target network in reinforcement learning? So it's this. So we have target network, which is the and also Q value estimate network, right? And in back propagation, we are updating the weights of Q value estimate network, right? So as a result, I've used W prime here, W bar here. Then what is the derivative of this with respect to W? Now my network, which is changing, is the Q value estimate network 1. So basically, it becomes by chain rule, simple derivative. And this term is constant with respect to W. Now, the target now doesn't move, right? Assume you are going after someone, but you will you don't let them move. You using some chains and these things. So right? Okay. So this is gradient Q learning. Initialize. W and W bar. Okay. And so two networks observe the current state S while not converged, select and execute action A. Again, either using random action or maximum best action in exploration, exploitation. Observe the new state S prime. Update. This step means backpropagation. One step of gradient descent, because we know backpropagation is nothing but gradient descent and chain rule. Okay. So whenever in the literature they say one step of gradient descent, they mean one step of backpropagation. Okay. And then here, this is one step. So this is the gradient and one step of gradient descent or backpropagation. And then you go to the next state. Okay. Then, but you need to, after every k iterations, what do? You let the target also be updated. So you fix it periodically. You fix it for k iterations, and then you change it. You let it change a bit, right? Because Q is also was supposed to have W in it, but you fixed it with chain, right? But now open the chain after every k iterations. Okay. So after every k iterations, update W bar. And how do you do that? You can update it either by optimizing W bar in the target neural network, again, using backpropagation in that neural network, or this is my suggestion. I didn't see it anywhere, but replace W bar with W. So copy the weights of the network of the Q value estimate to the network of target network. Okay, because they were supposed to be the same W. Yeah, I think we are out of time. We'll continue this in the next session. Thank you. Thank you.